Okay, so hey guys, welcome back to the channel. So we currently have three concurrent viewers, and I guess I'm the one among them. Okay, is the stream clear? Is the quality clear? Okay, so let's start the post contest discussion. So we would be solving three problems from today's weekly contest. Sorry, it's the bi-weekly contest. Okay, so should we go over the questions? First, the problems of the bi-weekly contest. Okay, so let's start. Yeah. So the first question is equal score substring. So the question states that you are given a string S consisting of lowercase English letters. The score of the string is the sum of the position of its characters in the alphabet. Okay, so if A is there, then its position is 1. Then for B it is 2. So similarly it is the same for all the elements. Okay, then determine whether there exists an index I such that the string can be split into two non-empty substrings, okay, that have equal scores. Okay, so we have to return true if such a split exists, otherwise we have to return false. And the substring is contiguous non-empty sequence of characters within a string. Okay, so here for this A and D, the value is 1 plus 4, which is 5, and for C and D, which is 3, C and B, which is 3 plus 2, which is 5. So yes, we can return true because we can divide this string into two substring such that it is having the same score. So it is basically, if we see, it is something like we are given a string. Let's say this is a string, and we have to find a position such that this string and this string, like if this substring and this substring is having the same score. So how we can do this? We can just iterate through this complete string, and we can calculate some total value of this complete string. Okay, for all the characters we can add its position so that we will get some total. So the total is over here. Okay, from this 0 we have this total. Then what else we will do is we will again start iterating this complete string. Okay, then for every point we will check if this 2 into my this is equal to total, because this means that this is the half position we have traversed. And if we encounter any case where we have traversed the half of this string such that this part is equal to this part, which is our score, or this our current part, equal to total or total by 2, we can do this total by 2, then we got our answer. Okay, or simply 2 into the score equal to total, then also we got our answer. So yeah, we did the same thing here. So let me show you the code. This is an easy problem, so let's not waste some more time in it. So we first calculated the total. So here we get the position of the character in the alphabetical order as let's say we have some character. Let's say A has some SK value and B has some SK value. So here we want the difference between them, so it would be basically B minus A. Okay, so B minus A, which will give me 1. Okay, so the index which corresponds to B is 1 and here A is 0. But what we want is, we have A as 1 and B as 2 in our question, so we will just simply add 1 to it. So this is what we do here. So we do C minus A, that is the character which we are looking for the index, and we do it that character minus A, and then we add +1 to it to make it one based indexing. In this way we calculate our total, and then we calculate the current, as basically we will just again traverse this string, and again we will maintain a current variable which will store the addition of the indexes of all these elements starting from the first of this starting from the 0th index for this string. And then at any point if we see that this total minus current equal to current, which means that basically total equal to 2 into current, then we can return true, that we have traversed half of the string, or we have traversed the string such that the current sum of the alphabets is equal to the second half sum of this string. So yeah, then if this case is not encountered, then we can simply return false, because we didn't find any index such that our total string can be divided into two parts, that is the left part and right part having the same sum. Okay, so yeah, this was an easy problem. So let's go to the second problem. Okay, so the second problem is longest Fibonacci subarray. Okay, so you are given an array. Let's not see this answer. Okay, so you are given an array of positive integers nums. Okay, and a Fibonacci array is a contiguous sequence whose third and subsequent terms each equal to the sum of the two preceding terms. Okay, we'll just read this, and what we understand is we have some array. Let's say we have something like this. So it is the first element, second element, third element, fourth, fifth, sixth. Okay, so here it is mentioned that starting from the first element, what it says, contiguous sequence whose third and subsequent subsequent terms each equal to the sum of the two preceding terms. Okay, this array is Fibonacci array such that starting from this is equal to the sum of this plus this. Okay, so I equal to sum of I minus 1 plus I minus 2. Okay, this is true for all the i's where I is greater than or equal to 3. Okay, here we are considering it as one based indexing. So this complete array follows this fashion starting from this third element. Okay, then what else is it is asked? It is said that return the length of the longest Fibonacci array, Fibonacci subarray in nums. Okay, so subarrays of length 1 and 2 are always Fibonacci. Okay, and the subarray is contiguous non-empty sequence of elements with an array. Okay, so when we have this complete array, there may be a case that there are some more elements, and here for some elements this element does not follow this property, like the sum of this guy may be not equal to the sum of the value at this guy may not be equal to the sum of this and this. Okay, so the contiguous part is this part, and maybe later we can look at this position if it contains a Fibonacci subarray. Okay, so in simple terms we are given some array, and we have the definition of Fibonacci subarray as like this. So we will have some Fibonacci subarrays in this complete array. Okay, and we have to return the length of the longest Fibonacci subarray. Okay, we have to return the length of the longest Fibonacci subarray from this complete array, and we have two more cases that the subarray of length 1, like this first element and the second element, is always a Fibonacci subarray. Okay, so we know that we have 2 as always our answer, and here n is okay, so n is the length of the numbers is minimum, it can be 3. Okay, so the answer 2 is always there. We will find always an answer which is greater than or equal to 2. Okay, so what we can do is we can calculate such position which holds this case, like the continuous positions which holds this case, and then we can keep the running maximum to calculate the maximum subarray which is having this case. Okay, so what we basically do is we have some maximum and we have some current. This is a standard setup, and then we just iterate through this array. If we encounter such condition, then we will just increase our current, increase our current, increase our current, increase our current, again increase our current. But once we see a case where the condition is not satisfied, okay, then we will just fill our max. We'll just fill our max. We can here or fill, we can fill our max here, or maybe we can just fill the max while we are calculating our current. So max will contain the maximum value, that is this value. Okay, now since this is we are not maintaining the continuous fashion here between these two subarrays, then we will just initialize our current to 0 again, and then we will again start from here to calculate the subarray, like the length of this subarray, which again holds this condition. Okay, in this manner we can go through this complete array while calculating our current, and at the same time we will keep the track of the maximum. Okay, and at the end we can just return the maximum. So let's see the code. So it's also a simple code. So what we do is we keep the maximum, we keep the current, then we will start from this second position, second index. So it is basically 0 1 2. Okay, that is the third element. And what we'll do is we will check if this holds the condition, which is nums of I equal to nums of I minus 1 plus nums of I minus 2. Okay, if it holds the condition, then we will just increase our current sum. Okay, we will just increase our current sum, that we have found an element which holds the condition. Okay, and if it does not hold, then we will simply initialize our current to 0, because we know that now this is not holding our condition. So there may be a case where this can be a starting point, like all the elements after this may hold the condition. So let's calculate them, and in order to do so, we initialize our current to 0. Okay, and while we are doing, we will just calculate our maximum, and in the end we will return max plus 2. Why we do plus 2? Plus 2 because here it is mentioned that the subarray of length 2 is always Fibonacci. Okay, which means that the first two elements are always there. First two elements are always there. Or instead of first two elements, I would say let's say we are checking the conditions for these guys. So these are always present in this. Okay, even though they don't hold the condition, because here there is no enough element to calculate the sum. Similar for this. Okay, so now if we have an array and we have some elements like this, and if our condition holds from this part to this part, then we have to consider this also, because here the this is calculated based on this and this, but we cannot calculate this and this, because here again we are not considering this elements because they do not hold the same case. Okay, so they do not hold the condition. So we can take this, guys, we can take this, that is what it is mentioned in the question. From the third we are calculating the answer, but we have to take the elements which are before this. So we add plus 2 here, so then we will just simply return our answer. So yeah, the second question was also simple. Now let's go to the third question, and here it is an interesting question. We have a couple of approaches to solve this. Okay, so let's start solving this. So first let's go to the question. So here the question states that we have to design exam scores tracker. Okay, and here it says that Alice frequently takes exams and want to track her scores and calculate the total score over specific time periods. Okay, implemented exam tracker class and the exam tracker constructor, where it initializes the object of this exam tracker class. Okay, then we have a function void or void record. Okay, and we have time and score as the parameter, and Alice takes the new exam at time t, or I would say at time and achieves the score which is given to us. Okay, so here it basically says that Alice takes some exam at time t and has score. Okay, and we have total score. Okay, and we have to return the total score from start time to end time, which is inclusive. Okay. Okay, if there is no basically no score between this, like basically there will be, if there is no exam between this time, then we can simply return 0. Okay, and it is guaranteed that the function calls are made in chronological order, that is calls to record will be made with sorry, so calls to record will be made with strictly increasing time. Okay, so if we consider the time frame, then Alice took some exam, scores scored some marks and that exam on time t, and then maybe she can again appear to some exam later in time, and then we will get some record that she has some score on that particular time. So we have the time in increasing order. Okay, and again Alice will never ask for total score that require information from the future. Okay, if the latest record is called within time t, then total score will always be called with start time and end time, which is less than this t. Okay, so Alice will never ask for some uh, like the total score between start time and end time in future. Okay. Okay, so we are given this class. Now let's not go to this solution. We are just given this three methods. Here it is empty methods, and we have to just implement this class so that we can give the total score in the optimal manner. So the constraints here are interesting. So the constraints are time will be up to 10 raised to 9 and same score will be up to 10 raised to 9. Okay, so at most 10 raised to 5 calls will be made in total to record and total score. Okay, so how can we implement this? How can we even implement this? So let's say we have some time t1 and we have some score s1, then we have time t2 and we have score as t s2, and here maybe we have time t5 score s5, time t7 score s7. Okay, now in this way records will be inserted one by one, and between these and while the records are inserted, she can query for the total score from s to t, or I would say start to end, s to e. Okay, so how can we do this? How can we do this? Let's first see the utmost naive solution. Okay, so it would be when she asks for time s to e, let's iterate from this s. Maybe it is from s is, let's say, t2 and e is, let's say, t7. So iterate from this to this and just calculate the score and return the score. But what if we have n calls? What if n calls are made to this? Then we will go to n square, because we have to always calculate the total score by traversing this array. Like we will always traverse this array, and the array size will be 10 raised to 9 at max, and here it is said that at most 10 raised to 5 calls would be made. Okay, so at most 10 raised to 5 calls will be made to record and total score in total. So there may be a case where we will exceed this time. Okay, so we can't directly loop like this. So what can we do? What can we even do? What if we maintain some prefix, some kind of thing? What if we maintain some prefix kind of things? But if we maintain a prefix, normal prefix sum, like let's say a normal prefix array, then how will we calculate the answer on the fly? How can we even calculate the answer on the fly? like let's say for the first test case, let's take this first test case itself. Can we take this? Okay, so let's create a test case by our own. Okay, so let's say we have some time here and we have scores here. So time is 1, 3, 4, 5 and 7. Score is 10, 20, 10, 30 and again 10. Okay, so what if I first say that we have 10 on time 1, then we insert 20 on time 3, then we insert let's say 10 on 4, 5, 30, 7, 10. Okay, let's insert all of them, and then I ask for this and this. How can we efficiently calculate this? Again, as we do in the standard prefix sum, we cannot iterate and calculate the prefix sum at the start only, because what happens is like we are given new record on the fly while the calls are made to this total score function. So we cannot just simply calculate prefix sum only at the start or maybe some finite number of times to arrive at the solution for total score. So there has to be some smart way. Okay, so what we can do is, let's say we have for time 1 we have 10, for time 3 we have 20. So instead of adding 20 as it is, let's add it let's add it with the previous element, because we know that there cannot be any other element which will appear after this time, which can be inserted over here. Okay, so once an element is added over here, then we are sure that no element will be added before this time, because the time is in the increasing order which is mentioned in the question. Okay, so when we are adding this 3, we will add this 20 with this previous element, so it would be 30. Okay, so again when we will say 4, we will add this 10 with the previous element, so it would be basically 40. Similarly for 5 and 7, we will add this 30 with this, which is 70, and then for this 7 we will add this with this previous 70, which is 140. Okay, so now let's say we will again add some element, like at time 8, which is maybe 10, and again at time 9, which is let's say 20. Let's not add currently this guys with this, because these are something which will appear in the future, or I would say future elements. Okay, future elements. So we are just bothered about these elements right now, because here add record was called for all these elements, add record was called, and here at this position after this record is inserted, here we want the total score from, let's say we want 2 to maybe 7. Okay, 2 to 7. So what we will do, we want the start time as 2 and end time as 7. So what we can do is, we want the first element which is equal to this or greater than this, So here, do we want this 1? No, because we want a total score starting from this time 2. Okay, so we don't have 2 here. Okay, so we will not consider this one, but we don't have any 2 here. Okay, we don't have any 2. Okay, so we can take the next guy, we can take the next time, because 2 is not present. So hence I told that we want s such that it is greater than or equal to our start element. So s will point here. Okay, now the e is basically any element. Okay, so here we were having 7, so we want 7 or an element which is just less than this. Like let's say if 7 is not there and here it is 8 and we want 7, so we cannot take this. We want something which is less than 7, and here less than 7 is 5. Okay, so we know that this is nothing but the upper bound, because the element which is just smaller than some element, like than some mentioned element, which is upper bound of 7, which is 5 here. Okay, so we want the sum of these guys. Okay, but we know that up to this we have the sum 70. Now I want to include this, which means that I'll just subtract this part. I'll just subtract this sum so that I'll get this complete part, because this is, we have added this, so this is like in increasing manner, and we want from this to this. So what we'll do is we'll subtract this part, so 70 minus 10, which is this part, so we will get simply 60, which is the answer for this. Okay, answer for this, so which is 3 4 5, which is this, which is 20 plus 10, which is 30, plus 30, which is 60. Okay, in this manner we can implement this. Okay, so that is one approach. And for this, if we write some pseudo code, then what we have is we will have some times array. Let's say we have some times array. Okay, so let's have a times array, and then we have some scores array, and when we have add record, add time and score, we can just simply push back our time in this times array, and then we will just push back our score in the scores array, but we will add this with the previous score. Like if we have some scores array like this, and we want to add scores over here, we will add this add the score by simply adding it, like the score which we got, we will add this with this element, and then we'll put that into here. Okay, and then while calculating the total score, what we will do is we will simply go over this. We will find start. Okay, so we first have the start and end. So what we will do is we will calculate the lower bound of this start, or I would say lower bound of this start. Okay, and the upper bound of this end. And what we will do is the answer would be simply the scores at this upper bound position minus scores of this lower bound minus 1. Okay, this is the same case which we did here. Okay, so this was our lower bound and this was our upper bound, so our answer is upper bound minus lower bound minus this position. Okay, lower bound minus one position. Okay, so we got our answer, and we can just simply return this. So this was some easy solution for the third question, although I solved it with some another approach which was a bit complex approach. Okay, so that's why my rank is not good in this contest, because instead of this prefix sum, I just got to segment tree, and that too a modified kind of segment tree structure. And I initially thought that I can do it with the normal segment tree, but then the constraints were 10 raised to 9, and in segment tree we have a nodes as 4 into the number of nodes, and the number of nodes is 10 raised to 9, which will give us MLE, which is memory limit exceeded. Okay, so how can we code this using segment tree, like a modified segment tree? Okay, so let's see that approach. So what we'll do is, let's say we want to store some elements from maybe 1 to 10. Okay, we want to store some elements from 1 to 10. So what we will do is we will create a segment tree structure. So let's have some node here. Okay, and here we have 3 or 4 parts, I would say. The left node, the right node, and the value at that node. Okay, the value at that node, and maybe we can store the mid element. Okay, and the left boundary of this node and right boundary of this node. Okay, let's store these values. So we have left node, right node, then maybe the current element or the value, I would say the value, and again we have left boundary, right boundary, and then maybe we can store middle, although we don't need middle because we can just calculate based on this, but let's store it. Okay, so now what does left and right denote? Left and right boundary, what does it denote? Now let's say I want a sum from 1 to 10, then I know that this node stores sum from left to right, so I'll get the sum here only. I don't need to traverse further in this tree. Okay, so I'll get my sum here only, so that if I came across a condition where all my elements are present in the current node, then I can just return the value from here. Okay, but let's say I want the answer for, let's say, some node 2, but here it stores the sum from 1 to 10. How can I get the sum for 2? Okay, so we will further extend this tree. How we will extend this tree is, the left node will store, let's say here we have from 0 to n, so here it will store from 0 to n by 2, and here it will store from n by 2 plus 1 to n. Okay, so in this manner we will just store the half of the values in the left and half of the values towards the right. So here again we will split this into half, so n by 2, this answer by 2. Okay, 0 to this, and again we will calculate the same for this, that is from n by 2 to this, whatever the boundary is. Okay, similarly we will do this. Okay, in this manner we will store all the values in this nodes, in the tree nodes itself, so that at max we will have n nodes, because each node contains one specific value, so at max we will have n nodes. Okay, so when we have to add some element here, we will just traverse this tree, and when we came across a condition such that this node contains only one element, that is the left boundary, and the right boundary is same. If left and right boundary is same, which means that this only stores only one element. Okay, so we can just store this element here, like whatever the element we are storing, we can just store it over here, and while querying we can see, as I mentioned previously, we will check if our element lies, like if all the sum which we want lies in this element, then take here, or let's go to left part or right part, and then we will get our answer. This is slightly some advanced topic, segment tree, but let's get a grasp of it, so that you can just dig in more over here, and let's try to understand this segment tree by your own. Okay, so here I'll just show the segment tree code, because the prefix sum code was quite simple. So you can just go to this code. So initially what we do is, we will create a segment tree. Let's not go to this part first, let's go to this segment tree. So in this tree we store the left part, the right part, that is this left and right boundary, then we store the middle element. Okay, and then we store the left node and right node, and we store the value. This current is just value. We initialize this. Okay, then we'll just update. Okay, what is the update criteria? So if we know that the left and right boundary is same, which means that only there is only space for one element. Okay, so this is our value, and we will return. So the node contains only this element, we will return. But if it is not the case, then we will check if we want to store the element in the left part or the right part, based on the mid value. Like if I go to this again, here I have some mid value, and based on this mid I have divided the left and right part. This will be mid, because mid is L plus R by 2. Okay, so this will be mid, the mid. So when I come here, I'll check if I have to go to the left part or the right part based on this mid, because this is something like the mid is the place which divides it into left and right tree. Okay, so in this way we will traverse. Okay, and while traversing, if you see that the left node, we have to traverse to the left node, but the left node is not present, then we'll create a left node. Okay, so it will start from this extreme left and the medium part, the middle element. Okay, so in this way we will pass it, then we'll update the element, and we will recursively do this for all the nodes so that we can traverse our tree. And we do the same thing for the right part. Okay, once we do all this thing, we will calculate the current part. Okay, so let's say we have some tree, this tree based on mid. Let's say we go to this part, and we place some elements here. Let's say we place 3, and here it was already here 2 was already present. So when we return from here, what we do is we want the answer on the fly. Like, we don't want to traverse this tree again and again to get the answer. So we somehow want the answer for this guy to be present over here. Like, we want the sum for this guy to be present over here, so that when I traverse this tree, I'll get my sum here only. I do not need to go to this part and then further move ahead. So how I can store the sum here is, for this node, like for this node, I'll take the addition of this left value and the right value, and that's what we do here, which is if left node is not null, then let's take the value of this left part, and if right node is not null, then let's take the value of this right part. Similarly, we will query, like we will check if we have the answer on the left part or the right part. So let's try to understand this query method. I'll just give you an overview. So here we have something like this. Let's say it stores 1 to 10, it stores 1 to 5, and it stores 6 to 10. Okay, so I'll check. Okay, so I want something like, let's say I want 6 to 10, and let's say I'm going to here, I'm going to this part. Okay, so I see that the starting of this is greater than the ending of this, which means that this does not holds my answer, so I'll return. Okay, when I go here, I'll check that okay, my starting like this position, or maybe this lies in this, which means that this will give me my answer. So I'll get the current value from here, or I'll get the value from here, and I'll return it as the answer. Okay, this is what we do here. So if the node does not contains the value, I'll just return. If the node contains the value, I'll just return my answer, which is present here for this current node. And similarly, if I have something like, let's say maybe here it is 1 to 10, here it is 1 to 5, 6 to 10, then let's say here it is 1 to 3, and from 4 to 5, here also it is, let's say 6 to 8, and here it is 9 to 10. Now I want the solution, now I want the answer from, let's say 4 to 6. So I'll go here. Okay, I see that my 4 lies over here. Okay, I'll again go to here, this part. Now this will again store values for 4 and 5 individually. Okay, so again I'll go to here. Okay, I know that my answer lies somewhere over here. I'll go to this part. I'll see that my left and R is like, there is only one element, and my L is equal to my R. Okay, so I'll return this 4 from here. I'll get my 4. Now again for this 5 and 6, I'll go to here. I got my 5 because because the same condition, L equal to R, I'll get this 5. So I'll take this 4 and 5, add them up, and I'll return from here, and I want 6. So again I'll go to this part, here it is 6, and let's say 7 and 8, 3 nodes are there. So I'll go to this part, I'll just take this 6, and I'll return my answer. And I'm not going to this part, because again we will have this boundary conditions which we previously mentioned. Okay, in this manner we will go to left and right node and take the answer from there, and while returning we'll just add them up, so that we'll get the final answer. So yeah, you can I just gave you the overview for this segmentary based solution, but study this topic because this is used in most of the problems. So yeah, this is it for this video. Okay, so this is it for this video. Hey bro. So we have 4 concurrent viewers now, but we have already discussed all the solution. We have discussed all the solutions, guys. So yeah, you can go through this live stream and understand the problems which are there in today's bi-weekly contest. So yeah, see you in the next video.